What? Yeah, that's right. Yeah, no, it was not intended. It wasn't like a here's what I think of you, kid. It was, and it wasn't like it was just, I was just teaching my class and all of a sudden somebody, was it? Fire. But who was it? Anyway, somebody was like, fire, fire, fire. And all of a sudden I looked over and Isaiah's assignment was in flames. No, I marked what I could see and I gave him everything that had burned away. I gave him perfect on everything that I set fire to, but I marked around it. So he did pretty well.
Imagine it got all of them wrong.
Anyway.
Or didn't answer the questions.
Yeah, you might have got away with something. That's fine. That's, if I light your work on fire, I'm going to assume you did perfect on it. All right? Is that fair? That's a good. No, what if it were a test? Just speaking hypothetically. When you speak hypothetically, you say were. Okay, I'd like you all to be quiet now. So, for example, burning sugar. What is the formula of a typical sugar? C6H12O6. That's the formula for what basic sugar? Glucose. Yeah, good. And if we burn it, what are we really reacting it with? Good, very good. And from grade 11 chemistry, what will it produce? What are the byproducts of this going to be? Or just from common sense, just look at that. Those things all bashed together, what do we end up with? Water. Good. That's where all the hydrogen's going to go. And? Carbon dioxide. Very good. And this should look familiar because this is what happens inside your cells all the time. We call it cellular respiration. Very good. What would balance this? Okay. Okay. Very good. All right. And there's just one thing we're going to add here that we haven't talked about it before. Energy. So in this case, energy is released by the reaction.
What would you like me to do today?
Honestly, today is just kind of, if you wanted to empty the dishwasher and put that away, that'd be amazing. It is chaos land back there. I actually have a million things for you to do, but I'm not even organized enough to tell you what I need from you. Maybe in the back half, I'll tell you all the 2 huge shipments came in yesterday of stuff.
I know.
So I'm just
the boxes were
I know. So I'm working on it. It's a work in progress. I'm working on it. Anyway, to start with, if you want to clear away the empty dishes and then load anything else that's dirty in, that would be incredible. Okay. I think that is all clean and good to be put away. So when a reaction releases energy, we say that reaction is exothermic. That actually makes sense because exo means outside is correct. Whoever said that, well done. And thermic comes from thermos, Greek, which means heat. So this is literally a reaction that puts heat on the outside. All right, that makes good sense, right? And heat is the default form of energy in the universe, if that makes sense. If energy is getting released, unless it's something sort of very specific, heat tends to be what it ends up as. We'll talk about why that is, the entropic nature of the universe. But basically, energy likes to spread out, and heat is just taking energy and using it to make molecules move faster, right? Which contributes to them spreading out and spreading that energy throughout the universe. This is the laws of thermodynamics. Basically, the laws of how energy moves or how heat moves is that it tends to spread out among the universe. So a reaction that releases energy typically will release it as heat unless something is sort of arranged to turn it into some other kind of energy. If you think about your car, the purpose of burning the fuel in your car is to turn the motor and make the wheels turn. But if you go put your hand near the motor what's been running for a while, what do you feel? A whole lot of heat. Your motor in your car is incredibly inefficient. It turns most of the energy from that gasoline into heat, and just some of it into energy of motion, kinetic energy. But mostly it turns things into heat. Heat is kind of your default energy release. So this is a reaction. We burn sugars inside our mitochondria, inside our cell, in a process we call cellular respiration. What's the exact opposite of this reaction? That's true, but of this particular reaction, what's its opposite? Producing sugars, which happens in a process we call photosynthesis. And if you remember, in photosynthesis, a plant will absorb water from where do plants get their water? Yeah, the roots, the soil, good. And it will absorb carbon dioxide. Where does it get that? The air. And it will absorb energy. Where does it get that? The sun's light. Very good. And it will use all of that to produce what? C6H12O6. It'll make sugar. And what's left over? Oh, good. Yeah, that's right. Oh God, wherever. Just shimmy, just slide. I'm sorry. It's chaos now.
Is this balanced?
Yep.
No.
Oh.
Yeah.
So when energy must go into a reaction for it to occur, we say that that reaction is what? Endothermic. Heat goes in. Those weren't used. They should be clean. I have a test tube rack in there for you. One sec.
This is not needed.
Okay, so we have endothermic and exothermic reactions. The idea that a reaction will either require the input of energy or it will require the output of energy. Energy is either going to enter the reaction system and be absorbed, all right, or it's going to be released. How's that feel? Not too bad? Okay, so the heat created or lost during a chemical reaction will raise or lower the temperature of the system. But listen, it's important to understand, when we say it's absorbed, we don't mean, absorbed doesn't mean the thing getting hotter. If a reaction, look at me, this is so important. If a reaction system is absorbing heat, it's taking heat and it's turning it into something else. It's turning it into bond energy. Does that make sense? Which means that if something is absorbing heat, the temperature will go down. This is how your refrigerator works. It undergoes a chemical reaction, well, actually a state change reaction, but regardless, inside the fridge that absorbs heat. Then it pumps that fluid outside the fridge, reverses the reaction, which releases heat. And it just does that over and over again, so that it's absorbing heat inside the refrigerator, There's a fan that blows new air across it. Then it moves that reaction outside the fridge, undoes it, blows a fan across it, gets rid of that heat, and it cycles and cycles. So look at me. If a reaction is endothermic, if it's absorbing energy, the surrounding temperature will have to go down because that's the energy that's being absorbed. The surrounding kinetic energy of molecules, the surrounding temperature will go down. If something is exothermic, if it's releasing energy, then the temperature of the surroundings will go up. Does that make sense? Because when we say absorbing heat doesn't mean like, oh, there's more heat going into the system, it'll get hotter. It's not like that. It's saying the system is absorbing heat. It's taking heat from the surroundings, which means the temperature of the whole system is going to go down. That one's the hard one to conceptualize. It's easy to conceptualize that when a reaction is releasing heat, the temperature goes up. But the opposite of that must then therefore also be true. When a reaction system is absorbing heat, the resulting temperature of the system will go down. Down. If we're absorbing heat, then the temperature must be going down. That is a little counterintuitive. So you have to stop yourself and think. Does that make sense? In an exothermic reaction, the temperature goes up. But in an endothermic reaction, the ambient temperature, the surrounding temperature will go down. Does that make sense? Well, let's take a look. No, don't be sorry.
I tried like too many times.
Great costume, by the way.
Thank you. I spent so much on it. I didn't think. Kartik, get out. Get out.
Why'd you say hug? You heard me.
No, I heard it after. Oh. I don't want to repeat it.
I asked her if she ate something. Yeah, it was on. Do you know that my old water bottle has my neck and
Oh, there is no
I'm sorry.
justifying that.
You never know though. You never know. Because like on Halloween, people could like come up covered in blood and nobody bats an eye. But it could, bro. Think.
You're the only person who would
I know. No, think about it. Because like.
Are you plotting?
No, I'm not plotting. But like some people could genuinely be like a murderer and just covered in somebody else's blood. Nobody would care.
I'm just trying to justify murder.
We don't know what you do.
We
We don't
I
know.
sleep in my room by myself, mind you. I'm gonna make that clear.
This is not that
He
important.
can see like a
We
little
know.
bit. He's not fully blind. He can see like
We
a
know.
Get out.
He's like,
Wait, you have to select it right.
he's only partial.
What's that?
All right, so where was I?
Temperature down.
Um,
It goes down, it goes up.
you know, when I die and go to hell, and let's face it, it's coming. I think it'll be like
How does that
the day after a school dance, trying to teach and having somebody upstairs being like, no, the truth is when I die and go to hell, and let's face it, it's coming, it will just be a high school dance. That will be my eternal suffering.
Can I just ask how that topic started? I just want to know.
I was thinking, boy, that sound is really like grating. And I thought, boy, it'd be a shame to feel that for all eternity. Then I thought about eternity, and then I thought, but if you're a betting person, I don't know. I'm not a betting person. But
You should bet on the days. Make a parlay. Should you bet on the days?
that's my eternal suffering. That's just my current life.
We listen to you.
No, I know. You guys are lovely. Anyway, I wouldn't listen to me. So if you look here, we can measure this. We can use this. So
Are we gonna do a lab on this one too?
oh yeah, this unit will do a few labs. If time permits, God, if people will stop not being here for a billion things. Because it really, boy, the constantly being out of class is really killing. Like we have missed 2 to 3 labs that I would normally do in this class already, just because you guys missed so many days, and it's not your fault. They just keep scheduling stuff like, oh, let's just put it during academic time. It's really frustrating me. So I don't know. I'm so bummed we missed the aspirin lab. That's a really fun one and a really cool one. Anyway, so with care, we can measure the energy absorbed or released by a reaction. Thank you. And that's because we know how much energy it takes to change the temperature That's the worst handwriting I've ever done. Of certain substances. So a calorimeter is a really clever idea. It basically says, if we surround a reaction with water, so that if that reaction releases water, all that heat will be absorbed. Damn it, let me try this again. If we surround a reaction with water, so that if the reaction releases energy, all of that energy gets absorbed by the water, then all we have to do to know how much energy got released is see how much hotter the water got. Does that make sense? Look at me again. I want to make sure you get this. You know that that candle right now is an exothermic reaction. How do we know that the burning of the wax in that candle is exothermic?
Releasing heat?
It's releasing heat. Now imagine if you could put that candle in a sealed container and on top of it put a pot of water and put a thermometer in that water. As that released heat, if the only place that heat could go was into the water, what's going to happen to the temperature of the water?
It's going to increase.
It's going to increase. It's going to go up, right? And then if you knew the relationship between the temperature of water and how much energy it had absorbed, you could calculate how much energy had been released by that reaction. Does that make sense? Temperature and energy aren't the same thing, but they're related. Energy will make the temperature of a substance increase. Now, different substances can absorb different amounts of energy before their temperature changes. Does that make sense? We call that the specific heat capacity of a substance. But as long as you know that, you can do math. And by the way, it's easy to test that because, for example, an electric heater is 100% efficient. If you run an electric heater, 100% of the energy you put into it will turn into heat. Oh, it's still going. Okay, let's keep going. So, it's been like this all morning. So, here's the deal. Once the change in temperature of a calorimeter is known, it is possible to determine the energy gained or lost in joules. Because joules is the SI unit for measuring energy. Calculating this change requires us to know the mass and the specific heat capacity of the solvent in the calorimeter, which is most often water. The specific heat capacity is the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. Quiet! Quiet! Just be quiet! Put your hand down. The unit measure is therefore joules per gram Kelvin. Note ben, kilogram is often used in place of grams. You'll see that sometimes. So, if you look here, this has a list of materials and it tells you how many joules of energy it takes to increase by 1 Kelvin 1 kilogram of this material. Let me say that again one more time so we hear it. This table tells you that if I have a block of ice, it takes 2,100 joules of energy to make a kilogram of ice increase in temperature by 1 Kelvin. Does that make sense? So if you got a kilogram of ice and you wanted to change its temperature by 1 Kelvin, which is the same as 1 degree Celsius, then you would have to give it 2,100 joules of energy. Contrast that, what's something that is easier to heat up? Sorry? Who said air? Air is like a third as much, right? So if you are heating up ice and air, which one's going to, if they're absorbing the same amount of energy, which one's going to show a bigger temperature change? The air. Because a kilogram of ice takes 2,100 joules to heat up by 1 Kelvin. On the other hand, a kilogram of air only requires... Yeah. And this is why metals heat up very quickly, right? If you look, like platinum or tungsten or mercury, a lot of the metals we use for things, even say copper heats up, it changes temperature very readily. A kilogram of copper will increase by 1 Kelvin after absorbing only 390 joules of energy. On the other hand, water is a beast. It takes a ton of energy to increase the temperature of water. How much energy does it take to make a kilogram of water increase by one degree? 4,186 joules. Substantially more energy. This is why an empty pot made of steel on a stove will heat up very quickly. It only takes 450 joules of energy for every kilogram of the pot to change by 1 degree. On the other hand, a pot full of water heats up very slowly because water can absorb a lot of energy. Does that make sense?
Like, we can measure the change in temperature for substance, right? Can we measure, like, how much heat a thing is getting?
Yep. Exactly. Yes.
So does it like directly correlate? Like, so you know how we were talking about like ice and air?
Mm-hmm.
If they were both to get like, say, 2,100 joules,
Mm-hmm.
does that mean air would increase like by temperature 3 times as much?
Exactly right. Now, the actual thing that's going to happen is they're actually going to change temperature but you know this, right? Because, think about it. When the sun starts shining down on us in the spring, the air will get quite warm, right? But it may still be the case that there's some snow on the ground and still some ice in the pond and some ice in the lake. Does that make sense? And that's because the sun can heat the air up 3 times faster than it can heat that ice up. Oh. And it can heat the air up like what's the number? Like almost 6 times faster than it can heat the water up. Does that make sense? So when the sun starts shining down on us in the spring and the summer, the air heats up pretty quickly. The dirt heats up pretty quickly. Trees and things made out of wood will heat up a little bit slower than the air, but they'll heat up a little bit quicker. But if you've ever gone swimming in a lake in May, you note that even though the air has gotten warm, what hasn't gotten warm yet? The water. Because for it to change temperature, it has to absorb way more energy. So that was a great observation. Very good. Does that make sense?
Where are the blue thingies for these?
I don't know. If they're not on the wall for now, just put them on the center table and I'll take care of them. So, once we know the specific heat capacity and the mass of a substance, you can design this math equation yourself. If C equals how many joules to increase 1 kilogram of material's temperature by 1 degree Celsius, which is the same as saying by 1 Kelvin, right? They have a different 0 point, but a change of 1 Celsius is the same as a change of 1 Kelvin. If we know that, then the math is actually easy. If we want to know how much energy gets absorbed,
Or is this the one with the triangle?
I guess. Yes.
It's like
It is equal to MC delta T.
Yeah.
What does each of these things mean? What's M, presumably? Looking at our definition of C. Yeah. This is mass. And mass is going to be measured in kilograms or grams, depending on the situation. Right? You could use pounds, but we're not going to use pounds. You could use ounces, but we're not going to use ounces. You could use milligrams, but we're not going to do that. We're going to stick with grams or kilograms. 1 sec, okay? The energy absorbed, we're going to measure in joules. Sometimes we will measure it in kilojoules. If you're American, what would you measure energy in? No? Calories. They use calories. Calories just a measurement of energy. If you're an electrician, what would you measure energy in? It's the absolute worst. No, volt is a measure of potential difference, not energy. They use the world's most annoying unit, the kilowatt hour. Yeah, the kilowatt hour. That's if you're using a kilowatt of power for 1 hour. Well, that's just the unit they use. It's a stupid one. If you're British, and if you're a British HVAC installer, or if you buy HVAC equipment, what do they measure energy in? BTUs. Does anyone know what that stands for? British thermal units. So if you see an air conditioner saying that it has 2100 BTUs, those are British thermal units. All of these units sucks. We use the joule and the kilojoule, which is a much better unit of energy. C is that specific heat capacity that we looked at above. The specific capacity. And we got to watch the units on that because it will either be in joules or kilojoules per gram or kilogram, and then Kelvin. You got to watch out. You got to check this because this table has the units as what? Joules per kilogram Kelvin, but you'll sometimes find a table that is kilojoules per kilogram. You'll sometimes find a table that is joules per gram. I've never seen one that's kilojoules per gram, but you might find that, so you got to watch out. You got to check your units. Does that make sense? Be careful to make sure your units match. And then delta T, what does delta always mean?
change.
Yeah, so this is, therefore, the change in temperature, which will either be measured in Kelvin or degrees Celsius, which, because it's change, it actually doesn't matter if you work in Kelvin or Celsius when you're talking about change. Absolute temperature, it makes a big difference. But a delta T in Celsius is the same as a delta T in Kelvin, because the only difference between Celsius and Kelvin is where zero lies. Celsius has this stupid arbitrary zero, which is the freezing and melting point of water, whereas Kelvin has a true zero, which represents zero thermal energy. Okay, so Q equals MC delta T. So now, we need a little bit of math. There's calculators there if you need them. Welcome to the math portion of this course. Our equation today is Q equals mc delta T. And when 500 mils of water in an electric kettle are heated from 25 to 65 degrees, how much heat flows into the water? Now there's something you need to know. The density of water, does anyone know it? Is 1.0 grams per milliliter. Every milliliter of water weighs a gram. A nice happy accident that makes for nice math conversions. All right? So, when you do a physics problem, what should you do? You should always identify your given. What has been given to us? And of course, we need to know by the end of the time this is done, Q, M, C, and delta T. We're going to know all these things. Which one are we looking for?
Q.
We're looking for Q. Very good. That's what the question asks for. How much heat energy flows into the water? Q. Do we know M? Not directly, but indirectly. What do we know? We know we have 500 milliliters of water, and we know that every 1 milliliter has a mass of 1.0 grams. Milliliters will cancel with milliliters. That will leave us with grams, and the math here is obviously trivial. It is? Yeah, because every milliliter weighs a gram, so it's 500 grams. Good. What is C? You got to look it up. What is the C for water?
4186.
Okay, so C for water is 4,186, but we're going to be careful here. It is 4,186 joules per, no, check the table, kilogram Kelvin, which means we need to do what with this? We need to convert it to kilograms. So what do I want to cancel?
Grams.
I want to cancel grams, so where should I put it? What do I want instead? And how many grams in a kilogram? 1,000. Good. Which means this is going to end up being what mass in kilograms?
0.5.
Correct. And I'm going to assume that they actually measured this to the nearest mil. We don't know that, but I'm going to assume it. I don't want to work with one sig fig here. And then what's delta T? How do you calculate a delta? How do you calculate a difference? Yeah, delta just means subtract. Subtract the two temperatures. So delta T will just be T2 minus T1. That's the definition of delta, the second value minus the first. What's the second temperature?
65.
65 Celsius. What's the first? 25. And what is 65 minus 25? Sorry? 40 degrees Celsius. And that is the same as saying a delta of 40 Kelvin. Does that make sense? Now again, to be clear, that's only true if you're talking about a delta. It's only true if you're talking about a difference that they're equal.
Sorry.
No, you're fine. So are we ready to put this into our equation then?
Yes.
Yeah. Do we need to rearrange our equation? No, in this particular configuration, Q is what we're looking for. So Q equals, what's our M value? 0.500 kilograms. And listen, I don't know about your other teachers. I want your units at every step. All right? In fact, we're going to do dimensional analysis. We're going to make sure our units cancel. What is the value of C? Yeah. 4,186 joules for every kilogram that changes by a degree Kelvin. Not a degree Kelvin, just by a Kelvin. And what is our delta T? 40 what? 40 Kelvin. Okay. We're going to check our units. All right? We're good chemists. We know dimensional analysis. We have kilograms on the top and we have kilograms on the bottom. What will happen there? Those units are going to cancel. We have Kelvin on the top and we have Kelvin on the bottom of a fraction. What's going to happen with that? It's going to cancel. What will the unit of our answer be? Joules. This may seem stupid, but if you take the moment to do this, look at me, it will make sure that you don't end up with mismatched units, which is so easy to do. Does that make sense? So now we look at that and we say, okay, our units cancel. And then this is trivial because what's 40 times 0.5? Half of 40 is 20. What's 2 times 4,186? 8,372, right? And then because it was 4D, we put a 0 on that, so the answer should be 83720. Can somebody check that? And then, of course, assuming that these are all the correct number of sig figs, we're going to assume that things were measured carefully. How many sig figs is this? We're assuming. If they measured to the nearest milliliter, we'll say it's 3 sig figs. If this was measured, well, this was given to us, how many sig figs is it? And then even though this ends in 0, we know where this number came from. It came from the numbers 25 and 65. So how many sig figs is it? 2, right? We know that this is actually to the nearest whole number. So how many sig figs in our answer? So what is our answer? Yeah, 84,000, right? 84,000 joules. And what do we often convert joules to? Kilojoules, which would be trivial. 84,000 joules. If I want to not talk about joules and instead want to talk about kilojoules, what number would go there? Where? On the top? 1, which would give us what? 84 kilojoules. I don't care. Either of those answers is fine. Unless I said kilojoules. But if it just says how much energy, you can work in joules or kilojoules, yeah. Okay, good question. They aren't, obviously, right? So 25 Celsius would be, we just add 273.15, right? We add 273, so that would be 298 Kelvin, right? And then the other was 65, is that right? And if we add that to 273, what do we get? 338, right? Okay. Now let's do the subtraction of these, right? If you subtract the other way around, 25 minus 65 would be what? 40. Okay. 338 minus 298 would be 338 minus 298. Use a calculator if you need to. 8 minus 8 is? 8 minus 8 is? 33 minus 29 is? 4. Good. So the difference is 40. Now, why does that work? Well, the reason it works is that you're saying 65 plus 273 minus 25 plus 273. And what happens to cancel there? 273 minus 273 is always going to cancel out. So if you're doing a delta T, you don't have to convert from Celsius to Kelvin. If you want it, now, if that confuses you and you always just want to do the conversion first, whatever, go nuts. It's not going to hurt you. But that's why. Again, only true if you're doing a delta, only true if you're doing a subtraction. That was a good question. Does that make sense to everyone? Cool. How does that feel? Not too bad? Now, obviously, in this case, we're solving for heat energy. We could be solving for all sorts of other things, but this is actually the changing of temperature of water becomes one of the most convenient ways to track energy. Does that make sense? It's incredibly convenient to just surround whatever you're doing with water and see how its temperature changes, because you can use this formula and that can tell you how the energy in the system changed. Does that make sense? Obviously, if the water gets hotter, whatever's happening is releasing energy. Obviously, if the water gets cooler, whatever you're doing is absorbing energy, right? But regardless, it is super easy to throw a thermometer into water, see how its temperature changes, and then from that, figure out what the energy was what amount of energy was absorbed or what amount of energy was released. Does that feel okay? You just saying that to shut me up? Okay. In that case, I'd like you to try this one. We have ethylene, a 50% solution of ethylene glycol, which should appear on... Oh, I give you the specific heat capacity. Okay. Now, note our units. Be careful. What unit is this given as? It says it takes 3.5 joules to change a gram of this stuff by a degree Celsius. Watch your units. Because what we're going to do is we're going to shove 250 kilojoules of heat into 4 kilograms of this stuff. Does that make sense? And I want to know what temperature change you're going to see. If we shove 250,000 joules of energy into 4 kilograms of ethylene glycol, that has a specific heat capacity of 3.5 joules per gram Celsius, what will the temperature change be? If you want, absolutely. Absolutely. The one thing I'd say with that is you just have to be careful and make sure you know where those units live. For most people, you're going to have an easier time making these units match that. But mathematically, it makes no difference what unit you change. Good question.
Oh, so the kilojoules remain the same. So don't worry about the kilojoules, right?
Well, you gotta worry about it. This is in kilojoules. This is in. They got to match. If you want to change this number so it matches that, great.
If you look at multiply as 10 raised to 3, so.
Yep. I mean, it's all just multiplying, right? But make sure your units match. Doesn't matter how you make sure your units match, whatever your preferred mathematical approach is. I am going to always do it the same way, which is I'm just going to look at our C value and change everything to match it. But that doesn't mean that's the only mathematically valid way to do it. I just think it's helpful when a teacher shows one way of doing things, not when a teacher shows... I don't know if you find this. I always find when a teacher shows me the 5 different ways you can do things, then I find myself sitting on a test going, oh God, and I mix them into 4, me doing 4 different things at once, which ends up being horribly wrong. So I like to teach one way of doing things, but that doesn't mean there's only one way of doing things. There's a lot of ways of doing things. But I'm not a big believer in choice. I'm really like obviously like your body, your choice, you're like in that sense. But in terms of like educationally, I think it's a better way to learn thing to have a mentor who says, this is how we do it. And that doesn't then stop you once you yourself are an expert from going, actually, I like this other way better. But I think that teaching works best when you teach a way of doing things, not 15 ways of doing things. This is my hot take. Yes?
So for the 3.5, the joules are on top.
Mm-hmm.
But aren't they also on top for the Q, which would be the...
Yep.
So wouldn't that mean they're on the whole square?
Are they on the same side of that equation?
You don't rearrange the equation?
Well, of course you're going to rearrange the equation.
End up being divided
Exactly.
instead.
Yep, exactly
Okay.
right. Beautiful.
Okay.
Hi.
Would I be able to get your intention sheet? Have it.
I don't have it yet. Can I get to you by lunch?
I'm not here.
Oh, shoot.
I can fill in, like, if you have no, like, if you personally don't have any.
As of right now,
then I can just fill in
the
things
only thing on mine is the day of, is the 14th of November,
like the
which is a Friday. No, the 14th of November is trivia night.
okay, that's okay because it doesn't start until the 20th.
Perfect. And then whatever day the concert is. Those are the only 2. And the day before the concert would be ideal.
Yeah,
That's
I
it.
can put the 14th
Yeah.
and the 15th.
That's perfect. Other than that,
Or the 9th and the 10th.
yeah. Other than that, we're golden.
Okay. Do you have the sheet still somewhere? That I can still...
I do. As to where it's somewhere in this monstrous pile, I'm sorry. I'm sorry.
I'll bring another one.
Thank you. I'm sorry. Yeah.
The announcements had page down before you got here, asking to be your first here.
Oh, I bet they did. Thank you for waiting until one of my peers was here to tell me that. I really appreciate your timing and the way it makes me look amongst my coworkers. No, that's good. Thank you. Man, you're going to get a hard exam. Exam just got harder, team. You're welcome. Thank Angela.
I mean, I wouldn't have to have done
Thanks,
it.
Angela.
I got it on time. So initially it's your
Yeah, sure. Hey, that's fine.
Just for on that note,
Yeah.
I'm excused from it, right? I asked your boss to give you a raise yesterday. Don't you remember that?
The exam just got harder again, guys.
I'm assuming you didn't get
Okay. Yeah, I wouldn't give me a raise. I wouldn't give me a raise as dog catcher. Anyway, so there you go. I want you guys to do this one. See what you get. All right, try it out. I don't know how your algebra skills are, but this is pretty basic algebra, right? This is a very friendly equation. It's this thing equals these three things multiplied by each other, which means if you're moving anything, how are you moving it? What's the opposite of multiplying? Divide, right? So this is a nice, simple equation to work with. It's friendly. It's a friendly equation.
Why would you compare this? These two made it easier. These times.
That doesn't sound like somebody. What if she doesn't give you the chance?
I almost did get from the initial college. I think I feel like for 5 minutes and then I'd like get it. Like I've been mad at it.
Angela, you're such a vibe right now. Oh, thank you.
My mom gets mad a lot. So it's like that's great. I just kind of doing that. I don't make it worse. But like,
I have a question. In the question, it says like a 50% solution, and then it gives us like 4 kilograms. Am I supposed to like cut it in half because it says a 50% solution?
wait, hold on.
Question?
The first one.
So that just means it's 50. It's like watered down. It's like 50%.
But it's still 4 kilograms. That's the mass.
Yes, it's 4 kilograms is the mass. 50% is the density, or like the amount of
The
ethylene.
density.
The amount, not density. The amount of ethylene.
So it'd be 0.5 grams per milliliter. That's the density, because the density for water was like 1 gram per milliliter. Did you say, okay, I'm asking? You said
I don't know what you're
okay,
asking.
it's fine, it's fine.
50% is the mole value.
Okay, cool.
I think that's what it is. I don't hold it.
Angela, what are you doing with this?
I didn't say shit. Oh, okay. I feel you.
All right, what do we got?
Hey,
A question, that's what we got.
Do we all have an answer?
No.
Why not?
You tried to ask me how we're gonna.
Cuz isn't an answer. I want an answer. Go. 2 minutes. Yeah.
How is the temperature? Oh, no. That's a relevant question.
Excellent. Oh, one sec. Ah! Oh, I slept kind of funny last night, and I'll tell you, I woke up and everything was just like, meh. That's what everything was like. It was like, meh.
This whole class It makes it very hard to breathe out my nose.
I believe that, but it's a great looking costume.
It looks
You did very
so
well.
happy.
Tara, I love your hat. It's a great hat.
Is that right?
Did you make this or is this a purchase?
100% for I'm not that.
It's very good.
It still looks very nice.
It looks great.
Huh.
You convert that to jewels.
I
Good.
did not think I was going to get it in time.
It is an issue with the
Good job.
machine and sort. It's
Great
like,
work.
it can take a while for it to come in.
Okay, so when we approach a question like this, we should be looking at our given. What do we need to know by the time this question's done? What are all the things that are going to either be given or what we're looking for? Q, M, C, and delta T. All right. In this case, which one are we looking for? We're looking for delta T, which means we should know everything else. What's Q in this case? What's Q? That is a number we need, but it's not Q. What's Q? Q is the amount of energy that actually gets absorbed, which in this case is what? 250, which I know you did right because you've got it right on your sheet. So you're good. And that's kilojoules, right? What's M? Yeah, it's 4 kilograms. And then, of course, we don't want kilograms. We want grams. There's 1,000 of them. If you can do this in your head, you do not need to show your conversion. All right. Most of you are going to be pretty comfortable saying 4 kilograms is 4,000 grams, right? But if you're not, do the math, right? Kilograms will cancel with grams. We'll be left with grams, 4,000 grams. Cool. Do we like 250 kilojoules, by the way? Yeah, we want joules instead. We know there's 1,000 joules in a kilojoule. So this should be 250,000 joules. And what is C as given to us? It takes 3.5 joules to increase a gram by a degree Celsius, right? All right. The equation we work with is Q equals MC delta T, but what are we trying to solve for? Delta T. What does delta T equal? How do we isolate that? If we want that by itself, what has to move? Yeah, we got to get rid of M and C, which are currently being multiplied. The opposite of multiplying is dividing. So we divide both sides by MC. M will cancel with M, C will cancel with C, and that will leave us with delta T being equal to Q divided by MC. In other words, if we take how much energy was absorbed, we divide that by how much mass we were absorbing it, and divide it by how much energy each gram can absorb, it will tell us the temperature change. Which means that we are absorbing 250,000 joules, and that we have 4,000 grams of ethylene glycol with which to do so, and that each gram of ethylene glycol can absorb 3.5 joules. Okay, now, dimensional analysis. We have joules on the bottom, on the top here, and we have joules on the top of a fraction in the bottom, which means those cancel. We have grams in the bottom of this fraction. Then we have grams in the bottom of a fraction in that bottom fraction. Those will cancel. And then we have delta C in the bottom of the bottom, which is actually the top. So our answer will be in degrees Celsius. And this should be fairly trivial math. 250,000 divided by 3.5 is like less than 100,000, right? Give or take. And then divide that by 4,000. This should be a little less than 25. This should be like low 20s, maybe high teens, like 18, 19, 20. What do we get? 18? 17 point. Give it to me fully.
8.57.
Okay, 8.5 is 8.6 is fine. Now, of course, if we track sig figs, this is how many sig figs? We're going to assume 2, right? And then this is only 1 sig fig. This is 2 sig figs. So our answer obviously should be to 1 sig fig. So our delta T will be 20 degrees Celsius, or if we prefer, we could say 20 Kelvin. Yeah.
Would it be like wrong if I were to keep the mass as kilograms, but turn like the capacity into kilograms?
No, that's totally fine.
I'm out of room.
Some of those probably come from Boehner. Find crappy looking ones and take them out, and then because those ones both look pretty nice, like there's no tape on them or anything. Pull a couple crappy looking ones out, put them in the back, and I'll go relocate them. Thank you so much for your help. I really appreciate it. How's that feel? Not too bad? And we should end with a sentence. Therefore, the temperature of the ethylene glycol solution will change by 20 degrees Celsius. So this is a bit of physics, but it's pretty friendly. Can we all agree that's not too bad? How's it feel? How many of us would say we're like awesome, amazing? How many of us are like, man, I love algebra, was so looking forward to algebra, couldn't wait for it, and now I finally have algebra? How many of us are like, you know what? I feel okay about algebra, don't love it. How many of us would say I hate algebra with the passion of 1,000 burning suns and this stresses me out? That's okay too. This isn't an algebra course, but realistically, if you want to do physics or chemistry, you're going to come across some algebra. The big thing to note here is do the given thing, write down what you know, do the equation thing, rearrange it. This one, you're only ever going to be dividing. The trickiest thing is making sure those units match. That can be kind of scary. It can be intimidating. When you're working on stuff, don't be afraid to throw your hand up and ask, like, hey, have I got my unit set sorted right? Or hey, have I done my algebra right? I'll coach you with that. I want you to know it, but this isn't an algebra class. Like I can help you. Yeah.
That was almost really bad.
You're good. You got this, kid. Yeah.
So I did the thing where I kept the mass the same and changed the capacity, but I'm still getting like a different answer. But it's like the same. It's just
you would have to keep both the mass and the Q. Neither of them matches, right? Or did you change this one to 250?
I changed the Q as well. I have to keep the Q.
Well, you got to be careful. You got to make sure everything matches. So if you're getting the wrong answer, which is to say you're getting the right answer, only it's like 1,000 times too big or 1,000 times too small, you've made a mistake in matching your units. So you gotta do so more carefully. My advice: don't try to change the C because you're probably doing it wrong. Because you have to remember that, like when it comes to C, grams is on the bottom. So if you want to convert this to kilograms, you're not going to divide by 1,000. You're going to multiply by 1,000 because that would be like going 3.5 joules per 1 gram degree Celsius. And so if you want to change grams to kilograms, where are you putting grams on this one?
Bottom.
No.
Oh,
Top. And what would you put? And you'd put kilograms there, right? So you can do that. And if you then want to turn joules into kilojoules or whatever, you'd put joules on the bottom, kilojoules on the top, like whatever. But note that you have to be careful about it. So to me, why change that one when all the other ones you don't have to be careful about? So you see what I'm saying? So can you change C? Sure. Mathematically, absolutely. But you're way more likely to make a mistake changing C than you are changing anything else. So why change the one thing that's tricky where there's units on the top and the bottom? If the answer is, I'm a mathlete and I want to flex my stuff, well, don't let me stop you. But I wouldn't. I'm pretty good at math, and my instinct wouldn't be to change C. I'm going to likely make an error. Those go. Ready? No, don't be scared. Look here. You see the map?
Yep.
I actually have them. I've got them. No, where are they? They are right over there. Right over there? But now I don't know where my damn thing of Sharpies is. But I will commend that to your use. All right, can we try one more before I send you off with your homework? Yeah. A cook heats water from 20 degrees to 50 degrees Celsius. Calculate the mass of water that could be warmed by the addition of 8.00 kilojoules of heat. So we know that it's water that we're heating. Have at it, team. Oh. Oh, I got a couple of people still to write a test, by the way, but if you want to see how you did on your test, you can check in with me once we've done this question. Can I take a look?
Sure.
I don't have my glasses today.
Okay, if it's wrong, I'm so sorry.
No, I'm not laughing at you. I'm
Oh.
just laughing at looking over and seeing somebody in a tall, pointy hat and with a cape spraying something in my back room by a bunch of... I remain very pleased with my period 1 jack-o'-lanterns. I think they did a lovely job.
Is that the whole assignment?
It wasn't really an assignment. They were a couple of days ahead of schedule. They're a nice group, so I said, why don't you make me jack-o'-lanterns?
Like, if we were ahead, you would have let us make
Yeah, but you're not ahead. You're days and days and days
No.
behind. Which, again, isn't your fault. But yeah, no,
Just be one more day behind.
I'm dying here.
Ooh.
I mean, we're all dying, but I mean, like, I'm really struggling with how far behind we are.
3 in 1 lesson.
3 in 1 lesson. The lessons aren't the issue. It's trying to get the labs in, right? Because you can't, like, I can sneak lessons together, right? Like, that's whatever. Like, that's exactly, I don't do 3 in 1, but I do kind of 1.5 in 1, another 1.5 in 1. Like, I can get you caught up on lessons. It's the hands-on stuff that is just
Teach the
brutal.
lesson and lab together.
I'll keep that in mind. So joules per kilogram Kelvin. So we need that to be joules. You've turned it to joules. Awesome. A delta of 30C is the same as a delta of 30K. Good. Q equals MC delta T. M equals Q over C delta T. Agreed. Yeah, that looks beautiful.
So far, there's only one lab that we did that they didn't do.
Yeah, I didn't make great time with you guys either. It's been a frustrating couple goes of it. But it's like, it's this model where they've switched school.
Yeah.
The big thing is the model of switching sports to these during the day tournament models. It's just killed my classes because the kind of kids who take senior U level stuff are the kind of kids who are involved in everything. They're the kinds of kids who are going and playing sports, which is awesome. But it just means like my classes get decimated every time there's a tournament. And then doing all of these like university fair stuff during the school day, it's killing me. Yes.
You know how I was not here yesterday?
Yes.
I did the test.
Yeah.
Can I do it period 4?
Yeah, that's
class period 4?
No, that's fine. 4 is
Have
great.
you marked them yet?
Yep.
Can we see our grades?
Yep. Oh, for you, bio. I'm finishing bio. I'm hoping to have them done by 3rd period. If not, they'll certainly be done by the end of the day. Sorry, yesterday I tried to mark them during the dance, but every 2 seconds people were talking to me, which is very sweet, and I didn't want to discourage that. But it did make for a very, very ineffective marking, right? Like, normally I can blast a set of unit tests out in 2 hours. I got like 2 tests marked in 2 hours. It was because people just kept coming over, chatting, which again is fine. All right, let's do this one quickly just so we all have it in our notes because you got your homework there. What is the Q in this case? How much energy are we transferring? 8.00 kilojoules. Good. What is the M? That's what we're trying to find. What's C in this case? What's C in this case? 4186 what? Joules per kilogram Kelvin, right? So, we're going to have to turn this kilojoules into joules. How many joules in a kilojoule? How many joules in a kilojoule? 1,000, good. Which means that this is 8,000 joules, right? And then what's our delta T? 50 degrees Celsius minus 20 degrees Celsius. So, what's that difference? 30, good. Which is the same as saying 30 Kelvin. What will M equal here? If I want to get M by itself, what do I have to move? Which I'm going to do by dividing. So we will get M being equal to Q over C delta T, which means we can say our mass will be Q is 8,000 joules, and that's going to be over 4,186 joules per kilogram Kelvin. And what was our delta T again? 30? So this is basically going to be 2 divided by 30. 2 divided by 3 would be 0.67, so this should be 0.0686, somewhere in there. 0.064. And we'll call that what unit? This is where we got to look carefully what units cancel. Joules cancel with joules. Kelvin cancels with Kelvin, which leaves us with kilograms. This isn't probably a good unit to report this in, so what should we convert that to?
Grams?
I would say grams. There's 1,000 grams in a kilogram, which makes this, 64 grams. If you wanted to leave it as 0.064 kilograms, that's not wrong. But I would say if you're answering a question, that would be a strange one. Any questions about that? All right. So then where that leaves us is you've got some homework here. I threw some way back ones in just to make sure we can still remember how to do that. That's important. You got to remember old stuff. Make new friends, but keep the old. Some are silver, the others gold. That's what they say. Well, that's how I feel about chemistry skills. Develop new chemistry skills, but keep those old ones, team. Any questions about that? Okay.